So today we have Fabio Apruzzi. Tell us about higher form symmetries, TFTs. Take it away.
Well, thank you for inviting me to speak again at the Quiver Meeting. It's a pleasure to be back and tell you about this recent progress that I've been working on in the last year. And yeah, so we talk about higher form symmetries and these topological field theories. And let me tell you what a symmetry TFT is. So a symmetry TFT is a topological field theory, and in particular is a topological field theory defined in D+1 dimension, in D+1 space-time dimension. And this theory is particularly meaningful when the space-time has a boundary. So we have a D-dimensional boundary. And in particular, it can encode two key aspects of quantum field theories of the D-dimensional, of the theory living on the D-dimensional boundary. And these two key aspects are the following. The first one is that it encodes information about the higher form symmetries of the quantum field theory living on the boundary. And it can encode also the Toft anomalies for this symmetry. So these symmetry TFTs in general, they can encode the information about all the symmetries of the quantum field theory, but I will focus on higher form symmetries and their Toft anomalies. So let me broadly motivate what this is useful for. So in D less than equal than 4 dimension, we have two inspirational questions, which are, first of all, can we describe the strongly coupled phases of quantum field theory in less than or equal than 4 space-time dimension in terms of a realization of symmetries? So this is a little bit the Landau paradigm. And in particular, these phases, can they be described by the order parameters for these symmetries? And whether, for example, the order parameter takes certain expectation value and whether the symmetries are broken or not broken. But however, if we use just the standard notion of symmetry, this is we soon realize that this is not enough. And I mean, in the past years, this generalization of symmetries, well known very well, has been given. So this new notion of symmetry that can describe, for example, confinement and deconfinement in Yang-Mills theories by the fact that the Wilson loop has perimeter area law. And moreover, Toft anomaly matching is a very important principle because a Toft anomaly, since it's a robust quantity, must match through the RG flow. And therefore, we can try to understand by Toft anomaly matching whether the infrared description is described by gapless mode like CFT or free theories or a topological quantum field theory. But what about higher dimension? In higher dimension, the situation is completely different. So the Lagrangian theories that we know are good in the infrared and are good in the sense that only they can be effective field theories of something more non-trivial that is happening at high energy. And we have many evidence from string theory that there are ultraviolet strongly coupled supersymmetric theories, and in particular, for example, supersymmetric CFTs in 5 and 6 dimensions, and or other type of theories like little string theories. And these are all predicted via string theory construction. But the non-perturbative dynamics of these theories become very complicated in the UV because there are new light degrees of freedom that appear in the UV, and they somehow change the theory. And in particular, they can also, like all we know is in 5 dimensions, they also change the symmetry of the theory. So some goals in higher dimension is indeed to understand these symmetries and how these generalized and standard symmetry of the full symmetry, the full symmetries for these theories, how they can provide organizational principle for the non-perturbative or perturbative spectrum of states, and in the case of generalized symmetry for the extended object that are present in the theory. And one of the questions is also, what about anomaly matching? What about Toft anomalies and whether they can have dynamical consequences for these UV strongly coupled interacting theories in higher dimensions. Okay, so the outline of my talk.
I imagine that by Toft anomaly, you just mean global anomalies, right? So the ones that existed long before Toft.
Right, anomalies for global symmetries. That's what I'm.
Yes. No, the Adler-Berdinjakiv anomalies.
Yeah. I didn't understand.
Adler-Berdinjakiv anomalies, which
that's not a Toft. That's that's not a Toft anomalies. That's it's because it depends on dynamical operator of the theory. Right?
Yeah, but I mean there is no difference. I mean it's a distinction between there is Toft anomaly matching, but no such thing as Toft anomalies. Bad use of language, simply.
Okay, but yeah, what I mean is anomalies for the global symmetries. Only global
anomalies.
symmetry. Only global symmetry.
Yeah, anomalies. Let's call them with their name.
Yeah, sure. So the outline of my talk, and I apologize for people who have been recently in this conference in IFA, so this talk would be much big overlap with that. So, but the outline of my talk is I will start by the topological definition of symmetries, and I will highlight the general procedure for obtaining these symmetries TFTs. And then I will proceed by example. And in particular, I will proceed by, I will start with a very famous example and we'll proceed with less famous examples in order to get the symmetries TFTs for these other examples. So we'll do the symmetry TFT for 5D n equals 1 SCFTs. And also, I will also tell how to derive this symmetry TFT from another perspective. So this is more a UV approach, and I will tell you an infrared approach on how to derive these symmetry TFTs. And finally, I will comment, if I have time, on properties of the boundary of the QFT living at the boundaries of this symmetry TFT that can be extracted indeed for these symmetry TFTs. So let me quickly introduce generalized symmetries. So, well, I guess by now you might be very familiar with this, but in order to set the stage, let me tell you how this generalization of these IF4 symmetries are defined. So for continuous IF4 symmetry, so what you have is a generalization of the standard current and the standard conserved current, and now you have a P+1 form current, which is constant. From this current, you can define on spatial slices the charge by integrating the Hodge star of this current. So in this case, you integrate on a d-1 dimensional surface, whereas for a generalized symmetry, you integrate on a d-p-1 dimensional surface. From the charge, you can exponentiate the charge in order to define the symmetry operator, where now so you can exponentiate the charge, and this is a symmetry operator, and this symmetry operator is a topological operator. So it doesn't depend on the deformation of this, surface or space sigma. In general, well, more than general, specifically, in order or in certain cases, let me say this topological operator, they behave under a certain group law, and the group law, which is given by the group element G. So you can multiply two different topological operators, and what you get is a topological operator which is labeled by another group element G double prime. So then this works also for this generalization for P4 symmetries as well. But what defines a symmetry that acts non-trivially on your theory is the action of a charged operator of your theory. So for example, a standard symmetry, acts on a point-like operator in this way, giving a phase with a charge of this under the symmetry of this operator. And whereas for an IR4 symmetries, what we have is a generalization of this principle, namely that the topological operator surrounds the extended object which is charged under this IR4 symmetry. So now if we try to compute the correlation between this topological operator and the charge operator, which is defined on a p-dimensional manifold, the crossing of the topological operator with a line will give this phase, where Q is the linking number between these two objects. So this was how higher-form symmetries are defined, but in general, for higher-form symmetries, the topological operator U have a group law. But it turns out that one can generalize this group law. And a first generalization is higher groups, where the topological operator U, so if you fuse two topological operators defined on this surface, sometimes it can appear a lower dimensional topological operator. So this means that different degrees of higher-form symmetry are mixing. But there can be another generalization, and which is very recent, and this is it's very recent in certain setup, but it was known for 2D Ising, for example. So these are the so-called non-invertible symmetries, and the fusion rule of this topological operator are more general, and where these are basically structure constants, and this now it's basically a fusion algebra, and not anymore a group law. So I'm highlighting these two generalizations. I'm not being very precise for them, but they will appear at the end of my talk if I have time. So that's why I'm highlighting these two generalizations of higher-form symmetries. But the main ingredient on my talk would be discrete one-four symmetries, and in particular the discrete one-four symmetries that are associated to non-abelian gauge theories. In pure gauge theory, without a matter or with only adjoint fermions, the one-four symmetry corresponds to the center of the gauge group. And it acts on a fundamental Wilson line in this way, where the phase is a root of unity over the order of the center of the gauge group. In the presence of matter, generically, the one-four symmetry breaks to a subgroup of this center. And this is due to an effect which is called screening, in the sense that matter can end on a Wilson line. And when a matter can end on a Wilson line, this topological operator U is not topological anymore. Namely, if we shrink the topological on the line, this can give a phase, but if we deform it by shifting on the right-hand side, this will give the identity. Meaning that it's not basically invariant under deformation. So this circle is not anymore a topological operator. So it doesn't define a symmetry. So what you can do with this higher-form symmetry, you can turn on certain background fields. And for example, you can turn on such background fields in order to study anomalies or other effects like spontaneous breaking of these symmetries. You can study the anomaly in infrared phases, confinement or deconfinement of these gauge theories in various ways. Okay, so let me now start with highlighting the general procedure for obtaining a symmetry TFTs, which is the topological theory that describes information about these symmetries, in particular in focus on higher-form symmetries and their anomalies. So the general procedure is given by, so if you have a geometric engineering string theory that engineers a quantum field theory, and or alternatively, you can have a brane setup which engineers this quantum field theory. And there are many interesting cases, from lower dimension to higher dimension. One of the, in many cases, one of the common features is that the background, so this geometry will look like a d-dimensional space where the theory, with a flat d-dimensional space where the quantum field theory lives, times a geometry which is a sort of cone, a cone over a d-1 dimensional link. In holography, keeping this cone is fine, but we can go beyond holography by deforming this cone to a cigar. And because what we are interested in are the topological information of the string theory reduced on this space. So I will tell you what I mean in a second. So in particular, we can derive a d+1 dimensional topological field theory by reducing the 10 or 11 dimensional supergravity where these geometries are defined in order to get this d+1 dimensional action. And we reduce only on the link L. We don't reduce on the call direction, but we reduce on the link L in order to get a d+1 dimensional action, which is topological. And in particular, we focus on the topological term of the 10 or 11 dimensional supergravity. So famous example is n equals 4 SUN super means. So we have n T3 branes probing C3, so flat space, and this holographically becomes ADS5 cross S5. So we have a radial direction, so C3 has a radial direction, and S5 is basically the link. And we have n unit of 5-4 flux, of course. And what we can do, one can reduce the topological action by doing these ansatz. So we're interested in the backgrounds for the 1-4 symmetries. So we're interested in keeping the background, so the B2 fields and the C2 fields. And this will be, the F5 flux will be only internal, defined on the volume of, defined on the S5. So this is a well-studied system. And the action that you get is this topological action. By the reduction on S5 of this action will leads to these 5-dimensional actions defined on S5, on IDS5. And what one can do with this action is studying the boundary condition as well as the equation of motion of this action and the quantization of this action. And what the boundary condition and the quantization of the action gives is specify the 1-4 symmetry or the line operator spectrum or the global structure of the gauge group. So for example, let me describe the two extremal cases. So we can choose C2 to freely vary at the boundary. Then B2 is an holonomy, which is the n value. And this is the background for the 1-4 symmetry, which is the electric background. And the global structure of the group, the gauge group, is SUN. Whereas if we do the other way, we let B2 vary at the boundary. What happens is that we have also C2 is now on a fixed holonomy, which is in Zn, and the global structure is SUN cross Zn. So this is what happens for n equals 4 square units. Another example, it goes beyond CFTs, and this is in particular, one would like to study the symmetry TFT for SUM n equals 1 4-dimensional superior means. So there is a string theory background which is related to SUM n equals 1 superior means, which is the Klebanov-Strassler solution in 2B. So this is dual to the infrared of the cascade theories. And in particular, the geometry is given by D3 brane probing the conifold, which is a cone over T11 that is topologically equivalent to S2 times S3. The number of D3 brane is K times M. And moreover, we have in the geometric engineering setup with M D5 brane on S2. This space can be viewed holographically as a 5-dimensional space with a boundary. And in particular, the rest of the space will be filled by this T11. And the branes will become flux now in the near horizon limit. And we have F3 flux through S3. And we also have F5 flux, which depend on at which stage of the cascade you are. Okay, so now what one can do is to reduce the topological to be action on T11. And reduce this topological action, also considering the Bianchi identity. And the ansatz that we implemented is this following ansatz, where we have H3, which is the freeform, the NS freeform flux, which has the background value times plus a fluctuating field on M5, same for F3 and same for F5. And the fluctuating fields, since we are interested in the 1,4 symmetry sector, are the derivative of B2, the derivative of C2, and also there is a derivative of another two form for F5. This is necessary for the Bianchi identities. Moreover, we would like also to activate the Rip vector, which is dual to the U1 isometry. That is the R symmetry of the 4D n=1 super Mills. And the R symmetry, this Rip vector, is broken down to Z2m by a Stuckeberg mechanism. So we have a U1 which is broken to Z2m by a Stuckeberg mechanism. So now we can plug in these answers into the expansion, and we can integrate on T11 on this action. And once we integrate, we get this topological action in 5 dimensions, which is our symmetry TFT, where C2 tilde is a combination of C2 and A2, where this is in particular this combination. Okay, let me comment on these symmetry TFTs. So the first term is similar to n=4 super Mills, and it's the term that you study in order to understand what is the global structure, what is the line spectrum, and what are the 1,4 symmetry of the theory. The second term is an anomaly term, and in particular, let's focus on one boundary condition. By varying, we vary C2 tilde at the boundary, and we fix B2 to be anomalies of Zn. So their periodicity of B2 will be integer mod m. And because also the periodicity of these AR are integer divided by 2n, the second term realizes a mixed Toft anomaly between the chiral symmetry C2m and the 1,4 symmetry. And this anomaly has a lot of consequences that I won't explain, but one can study Toft anomaly matching on this anomaly to constrain confining data of SUN super Mills, and which preserve the 1,4 symmetry because they're confining. And moreover, if one study also the infrared solution of Klebanov-Strasser, an extra term appears in the 5D symmetry TFT, which is a total derivative and correspond to a 4-dimensional TQFT that matches this anomaly. So this is just a comment, but we can ask me more if you want to know more about this at the end of the talk. And this is anomaly, a famous anomaly that was studied in these two papers as well, but derived only using Toft anomaly matching. So in this case, we used string theory to derive this anomaly. Okay, so going up in a less famous example, there is we would like to apply this for 5D n=1 superconformal field theories coming from 2B supergravity. But before doing there, let's do a warm-up example, which is 6D 1,1 liter string theory. So 6D 1,1 liter string theory is a theory which is engineered by N and S5 brane in 2B, and its holographic limit is a linear dilaton background. So we have a background, the metric of the background is this, where we have an S free, and we have n unit of free-form flux. And the lineator is as this expression, where rho is this coordinate. Okay, again, we implement an ansatz that realizes what we want to study, which are the backgrounds dual of the higher 4 symmetries. So the ansatz for F5 is this one, where F5 and F2 are filled in this in the 7-dimensional space, consisting of this flat 6-dimensional space times the rho coordinate. F3 will be only the external, so this 7-dimensional space, and H3 will have this background plus an external fluctuation. Okay, and this field, they need to satisfy Bianchi identities, and the solution for these Bianchi identities are the following ones. So F3 is equal to DC2, H3 is equal to DB2. This modified Bianchi identities tells us that F2 is equal to this expression, and F5 is this more complicated one. So let me comment on this expression. So B2 is a background for the U1 1-4 symmetry. So this is a background for a continuous 1-4 symmetry. And C2 is the background for a discrete 1-4 symmetry. This is because there is a Stuckelberg mechanism for this C2, which is represented by this term and its kinetic term. And whereas B2 is only, there is no Stuckelberg mechanism, and it's a background field for the U1 1-4 symmetry. So then you can reduce, so as a comment, this B2 U1 1-4 symmetry is basically, so this little string theory is a low energy effective field theory, which is a 1,1 gauge theory in 6 dimensions, and non-abelian gauge theory, which has a topological current, which is Hodge F wedge F, trace F wedge F, and this topological current is coupled to this 2-4 field background, which is a continuous because that is a U1 1-4 symmetry. Okay, so having done this ansatz, we can reduce this on S3, and we can reduce the topological action. Let me just, for simplicity, in order for satisfying gauge invariance, let me extend this, the 10D topological action of 2B through an extra dimension on 11 dimension, where now our quantum field theory will live on a double boundary of this 8-dimensional space, which is the reduction of this 11-dimensional space on S3. So we have two frames. We have two frames in this theory, which one is a BF frame, which are dual to each other, and one is a Stuckelberg frame. So Stuckelberg frame is specified by C2 having related by this related to DC1 to this, and also by the kinetic term of F2, which give us Stuckelberg mechanism for this this 1-4 symmetry that breaks this 1-4 symmetry to zero. The dual mechanism is this, the dual frame is the BF frame, where now C1 is dualized to C4 in 7 dimensions, and the topological symmetry TFT is given by this action. So this is the reduction of the topological term of 2B on this S3 sphere. In Stuckelberg mechanism, we don't have these. In Stuckelberg frame, we don't have this coupling, but we have only this coupling, which is common also to this action. And this coupling relies on a mixed anomaly between the two 1-4 symmetries of these theories, the continuous 1-4 symmetry and the discrete 1-4 symmetry, because C2 have anomalies in this, which are CN anomalies. However, there is something weird going on, and in particular, this action is not invariant under large gauge transformation for these C2 fields. So what one can do in order to fix this gauge non-invariance under this, especially for n odd, this is only true for n odd. So what one can do in general to fix this gauge invariance is to add a term that doesn't change the 7-dimensional equation of motion. And in particular, one can add a term which is proportional to the Bianchi identity, and by integrating the obviously total derivative term, we get a corrected term which corrects the 7D topological action in this way. And now this topological action is invariant under this gauge transformation and realizes the anomaly of this, the mixed anomaly between these two 1-4 symmetries. Okay, so let me go to the meat of this talk, which is the symmetry TFTs for 5-dimensional CFTs from 2B supergravity. And in particular, 5D CFTs are engineered. By the way, are there any questions on these warm-up examples? Okay, so we can indeed engineer 5-dimensional CFTs by using PQ webs. And PQ webs are webs of 5 branes, PQ5 branes, that extends they have five common dimensions where the 5-dimensional theory lives, and then they extend an angle in this plane, as many of you are familiar with. So we can consider this web, this singular web. So this is a web where all the compact phases are shrink to 0. And this web is dual to a toric diagram for a Calabi-Yau threefold, which is the M-theory setup. So you can engineer the same 5-dimensional theory using Calabi-Yau threefold, and in particular using this toric Calabi-Yau threefold. And this the diagram is just a dual toric diagram of this toric diagram. In particular, this example, it's not just a random example that I show you, but it engineers a 5D CFTs, which has a low energy limit, a low energy effective field theory description that is an SUP gauge theory with Chern-Simons level Q. So in 5D, we have Chern-Simons level, classical Chern-Simons level, and it has an integer coefficient Q. Okay, so this singular web, we can take this singular web, and this singular web can be indeed viewed as in the following way. So we can view this singular web as a call over a link, which is a 4-dimensional space. And so this web is a 2-dimensional times R3. So this is a 5-dimensional space. And so this is why this cone is a cone where the base is a 4-dimensional space. But we have extra ingredients on this cone, which are semi-infinite branes extending to infinity and pinching the space at infinity, so the boundary of this cone. And these are these non-compact 5 branes that will go to infinity and they will pinch the boundary. So this link has this following geometry: is a disk with puncture at the boundary of this disk, realizing the pinching of this 5 brane at the boundary, times S2. And this geometry, let me also mention that this is inspired by the holographic setup that was studied 4 or 5 years ago by this group. Okay, so we implement the same strategy as before, as we did for the 1,1 little string theory. We take the topological coupling of 2B. Again, we extend in one extra dimension in order to have like gauge invariant under the local transformation for these fields. We implement these expansion ansatz, and in particular, we expand on the non-trivial cycles of this 4-dimensional space. So the non-trivial cycles are free cycles, which are given by a semicircle surrounding these punctures times the S2. So these are the beta. And then we have also one cycle, which can be, for example, segments extended between 2 different punctures. So these are locally how this cycle can be represented. And then this cycle, they all must respect this global condition. So what are the backgrounds that we can deduce from these ansatz? So the background is there is U1 flavor symmetry, which is given by there can be many U1 flavor symmetry described by depending on how many punctures you have. But this is a combination of these of H2 and F2. The detail of this combination don't really matter much. So the detail of this omega, which is the intersection period between 1 and 3 cycles, don't really matter too much. But it's important to know the number and of these of the non-trivial U1 flavor symmetries. Moreover, we have also 1,4 symmetry, and 1,4 symmetry can be deduced from the charge, from the PQ charge of the 5 branes. In particular, the PQ charge of the 5 branes, if you want to implement an SL2Z covariant formalism, which act on this vector. So we can have an index, an extra index J, which is a label, an SL2Z vector. Then we can put the charges in this 2 by L matrix. And we can put this matrix in a Smith normal form by changing the basis of F3 and also the basis of this label by the index which label these punctures. And by changing the basis, we can put this matrix Q in a Smith normal form. And what we have in this case is that the Smith normal form will generically be of this kind, where we have 1, and we have the GCD of PQ, which tells us that the one for symmetry is Z GCD of PQ, when GCD of PQ is not. So to recap, the A1 tilde back is A1 tilde realized is a transformation. So we can apply the B matrix on the vector labeled by this index L, and this is the transform U1 background. And so the U1 background corresponds to the U1 flavor symmetry. And the C2 tilde background, which again is the transformation given by this matrix A acting on this F3, so the inverse in this case of this matrix A acting on this F3 vector, will give what is the background. So C2 tilde is the background for the one for symmetry. Okay, so now we can plug these ansatz and we can integrate all the link geometry, which is this disk times S2. And when we do this, we get the following expression. So in this case, let me just highlight the BF frame. So the BF frame, we have this the Bianchi identity, which is specified that G2 tilde is given by this expression. And so the one for symmetry will be Z GCD P and Q. This is due to S2 Quiver mechanism for these fields. But moreover, we have an anomaly term on the symmetry TFTs. And this anomaly term is a mixed anomaly between the U1 flavor symmetry background, which in this case is only one non-trivial, and is dual to this instaton current, and the one for symmetry, which has these anomalies. And this was also studied by using the gauge theory description in this paper a couple of years ago. Okay, but this is not the full story, because we have sources on the link geometry. So we have puncture, which represent sources for the link geometry. So we don't have, so the topological terms of 2B is not the full story. What we need to add are the topological terms, which correspond to the West-Ubino action of the 5 brane sources, which will contribute to the topological action, to the 6-dimensional topological action. There is a nice paper which tells us that there is a non-trivial contribution. And in particular, it tells us what is the SL2Z covariant West-Ubino action for this brane. And the SL2Z covariant West-Ubino action for these branes is given by this expression. So this is very schematic. So it's a very complicated expression, but it can be recast in a SL2Z product, which is represented by this dot. And Q is basically the PQ charge matrix, whereas C are the Ramon-Ramon forms, is the sum over all the Ramon-Ramon forms as a standard West-Ubino action. And then we have also this curvature background, which is expressed by this expression. So we can have a tangent space background and a normal space background, which realize the R-symmetry. These are important also for this discussion, but I won't give any further detail about this. But I will just show you the result, and the final action again is the anomaly term that we already got from the 2B topological term, plus a contribution which is proportional to C tilde cube. So this is an anomaly for the 1-4 symmetry. So anomaly which involve only the 1-4 symmetry. And it's not trivial because these the holonomy of C2 are the following, of C2 tilde are the following one. And again, this string theory results matches the one known from gauge theory. And in particular, this anomaly, the second part of this expression was derived in this other paper. But one can do more. We can do also examples which do not have a gauge theory Lagrangian description in the infrared, a non-abelian gauge theory Lagrangian description in the infrared. We will see that these theories, they can have a Coulomb branch descriptions, and you can derive this anomaly from the Coulomb branch description as well. But as long as if we want to consider a non-Lagrange gauge theory description, these theories do not have a Lagrangian a non-abelian gauge theory description. And in particular, these theories are all mass deformation of Tn. So, for example, we have Bn theories, and for n equals to 3, the B3 theories, these correspond to the E0 theory, the E0 cyber theory. And there is an anomaly for the 1-4 symmetry. So that theory is a 1-4 symmetry, which is Z3. If you plug in n equals 3, you realize that this is equal to 3. And the anomaly is given by this expression, and is non-trivial. But there are also other generalizations, and they also have these symmetry TFTs, and in particular, I'm only showing the anomaly term for these symmetry TFTs. Okay, so this concludes the part from this UV approach in order to determine these higher form symmetries, anomalies, and in particular the higher form symmetry TFTs. Before going into this infrared method, let me pause and ask whether there are questions on the UV approach. Okay, so if there are no questions, then let me describe how one can get the same symmetry TFTs by using the low energy effective field theory description. So possible low energy field theory description are 5D gauge theories, and anomaly have been studied using this 5D for 5-dimensional CFTs by using a 5D gauge theory description, as I told you. But 5D and CFTs have also a Coulomb branch description. So we can, for example, go into the Coulomb branch of the gauge theory by giving Vev to the scalar, which is in the vector multiplet. In 6D, we can have a low energy description, which is the tensor branch. And this will, especially for 1,0, will give vector multiplet coupled to abelian tensor multiplets. So this is why this is called tensor branch. And it's because we give a Vev to a scalar in the tensor multiplet. And all these anomalies are captured by d-dimensional free Maxwell theories or generalizations. So this is what I've been studying in this paper, and also there is a nice story in 4 dimension by using the BPS quivers in this paper as well. So let me highlight how one can compute the symmetry TFTs from the Coulomb branch description. So in the Coulomb branch, we have a gauge group, which is U1 to the power of R in general, where R is, for example, the rank of your gauge theory. And in general, the action for this gauge theory is given in 5 dimensions as a kinetic term. So this is only displaying the vector multiplet, not any method that can be present. So we have the kinetic term for the vector, and we have also Chern-Simons term. So by studying this action, one can realize that there is an electric 1-4 symmetry that looks like I1 because there is a current, although this current is not really a gauge invariant operator. So you can think this as more or less like an accidental U1, which is broken to a discrete subgroup by massive state, for example, the W bosons, which are massive in the Coulomb branch. And moreover, there is also a magnetic 2-4 symmetries, which is again an abelian U1, and this is given by this freeform current, which is the odd star of Fi. Its conservation is given by the Minkowski density. So we can activate backgrounds for these two higher form symmetries, and we activate backgrounds for this 1-4 symmetry and for this free-form symmetry. So once we do that, the action is the following one. So we have these terms. This is a term that is necessary. So we shift the kinetic term by these B2 field, the background fields, because the 1-4 symmetry action is also shift the gauge field in this way. And we have also a coupling between, this is a current of a background coupling. So we couple the free-form current to its background. And we also have the Chern-Simons term. So we have this Chern-Simons term. And again, we shift the F, the fist by this B2 background. And we can also have, if this is a Coulomb branch non-abelian gauge theory, then we can couple the theory to the U1 instant on background, which is the background for this standard 1-4 symmetry. For the standard 0-4 symmetry, which is a 1. So it's a current for the 0-4 symmetry. Okay, then we can implement the symmetry transformation on the background fields. And once we do that, we realize that the symmetry transformation can only be absorbed by this higher dimension, one-dimensional higher action, which is a topological action. So this one-dimensional higher action contains this term, which is a BF term, and it contains this Chern-Simons coupling, as well as this other Chern-Simons coupling coupled to the U1 instant on current. So for example, I'm highlighting the example of SUP, which example of SUP at Chern-Simons level Q, where Cij is the Cartan. The Chern-Simons level are given generically by these numbers, and by change of basis to Smith normal form. So we change our basis here. So we start from it. We change our basis to Smith normal form, and what we get. So this B2 will be base change vector B2 and B3, and what we get is this action. So this is the BF term, which one can study, of which one can study boundary condition in order to determine what are the symmetries for the boundary theory. And these are anomaly terms, the same anomaly term that were also derived by using the string theory approach, or like, for example, the gauge theory approach. So this Coulomb branch approach is an agreement with the previous results. So what about other examples? So let me show you some other interesting example, which is the minimal 61,0 CFTs. Minimal meaning that the tensor, there is in the tensor branch, you have one abelian tensor, which is coupled to a gauge vector. So this is the bosonic action. So I'm not displaying any fermionic part. So we have, this is the tensor multiplet, which consists of a scalar and a B2 field, whose field strength is H. And then we have the kinetic term for the vector field, as well as this topological coupling the dynamical B with the gauge field. So there is a 2-4 symmetry, which is J equal dB. And again, this is a 1-4 symmetry, which is accidental and will be broken by BPS strings, which are charged under this field P, but they only give massive state at the level of the low energy effective theory. And again, we can implement the same strategy. We can couple this theory to background fields, to the 2-4 symmetry background fields, C3, but also to the 1-4 symmetry B2. And by coupling this action to this background, we again get this shifted kinetic term. And we get this coupling to the one-form symmetry as well, which is given by the background fields B2. And we also have this coupling where the last term is basically a counter term, which is present. And again, we can ask what happens under 2-4 symmetry transformation. What happens to deduction under 2 symmetry transformation? And it turns out that there are ambiguities of this action that can only be reabsorbed by this one-dimensional higher action, which is given by this topological term times this term, which might look like an anomaly. However, one can study the boundary condition of this action in order to see how one can define absolute theories. Right, in 60 theories, they are not really quantum field theory in the sense that they don't have a partition function, but they rather have a sort what is called a partition vector. And in some cases you can have a partition function, but these are cases where, for example, n is a square, or we have a product of 2 theories. Anyway, just to briefly comment, if you study those cases, at least for rank for the minimal 60 CFT set, you realize that this term will not give an anomaly for the absolute theories. However, you can do one thing. You can do implement a circle reduction, and a circle reduction of the symmetry TFTs gives this 60 action. So this circle reduction means that the 60 theories now is viewed as a 5D theories, which is a KK theory. Is a KK theory, meaning it's a KK reduction of a 6-dimensional theory. So this is the symmetry TFTs for this 5D KK theory. And these symmetry TFTs can also be independently derived from the 5D Coulomb branch of these 5D KK theories. Okay, let me finally comment on some aspects of the QFT that lives at the boundary of the symmetry TFTs. And let me show you this last example, this last complicated example that I present you. So the first consequence is that, for example, we can study boundary condition of this action. And first simple boundary condition is we may be freely varying at the boundary. And this implies that B2 at is fixed, fixed at the boundary, and realize the background for the 1-4 symmetry, which is for the 1-4 symmetry of the 5D KK theory, which is a ZN field. And has these anomalies. We can do another thing. We can make B2 at freely acting at the boundary. And now we get boundary condition, and we get also this equational motion that tells us that the transformation of the B2 field will mix with the transformation of the B free field. So this tells us that there is an higher group structure in this case. This is sort of a discrete version of the. It's not really. This is basically a Stugerbeck mechanism. It's basically a Green-Schwarz mechanism, which tells us that we have a higher group structure in this case. But we can do one last thing, and we can do what happens if we vary B2 at the boundary. And if we vary B2 at the boundary, this should lead to what are called these newly or very recently studied non-invertible symmetry, which are of the type discussed in this paper. And in particular, for this example, they've been discussed in this paper. And there should be a way of seeing this non-invertible symmetry also from this symmetry TFT point of view. But in order to be a bit more precise about these non-invertible symmetries from the symmetry TFTs, let me go back to the 4D n=1 superior means. So 4D n=1 superior means has this symmetry TFT, which can be derived from quantum field theory in the UV, from the gauge theory description theory, or also from string theory by studying the Klebanov-Strasser. And again, we ask what happens if B2 is freely varying at the boundary. Well, it happens that the topological defect for the zero-form symmetry, which is the chiral symmetry C2n, now is not gauge invariant anymore, because we will have this sort of shift of this topological symmetry, a sort of anomaly on the defect, anomalous variation on the defect. And how this can be cured is by adding a topological quantum field theory on the topological defect for the zero-form symmetry, which cancels this gauge ambiguity, which cancels this object being not gauge invariant. And by doing this, we pay cost, and the cost that we pay is that this topological defect is not non-invertible anymore, as it was studied in this paper as well as this paper. But from a point of view of string theory, this is an interesting question, and is how this boundary condition can source extra stuff, in this case, this topological field theory that decorates the topological defect for the zero-form symmetry. Finally, let me go back to the higher group, and in particular, let me discuss a case which is the SU2 theory. And the SCFT correspond with low energy limit, which is the SU2. So we specify P equal to Q, and in particular, we specify P equal to, and there is no Chern-Simons level for SU2. So it is well known now that we have evidence that this flavor symmetry enhances to SO3, and we can study the charge of the BPS object, BPS particle that we have in this theory by studying the charge on the various symmetries or intersection numbers in M-theory abstraction, or some data of the two B webs, and we can study the charge on the electric charge or charges under various flavor symmetries of these theories. What this charge tells us is that the faithfully acting symmetry on this charge is this symmetry, is a U1, which is correspond to the Coulomb branch U1 gauge symmetry, times SU2. Well, in general, times U1, but when the masses of these two particles are equal, then we can enhance this to SU2, modded out by Z4. So it was argued in this paper that there is a two group for these theories, and two group which is basically a sort of related to the fact that that we have the structure group, and the transformation and the background of B2 have a sort of non-trivial derivative, and they correspond to the Bockenstein homomorphism for the W2, which is the W2 is the Stephen-Witting class for the SO3, which is the structural lifting SO3 bundle to SU. So this is nicely encoded into a sequence, and the Bockenstein homomorphism is basically a map between the cohomology of this sequence. I won't go into detail, but what one can study in the Coulomb branch of these theories, by activating, and again, by using this infrared method in order to derive the symmetry TFTs for this background, one can study whether there is a two-group anomaly for these theories using this infrared Coulomb branch approach. Okay, let me conclude by saying that symmetry TFTs are a useful gadget in order to describe the symmetries. I mean, I focus on higher form symmetries and their anomalies of various systems. And in particular, systems that are engineered by string theory geometry, and we can derive the symmetry TFTs by using these string theory geometries. So there are many cases that have been covered, but there are many other cases that can be covered from lower dimensional to higher dimensional cases. So the symmetry TFTs, and in particular, the symmetry TFTs that one can compute from string theory geometry, they match the one computed with other methods, for example, gauge theory descriptions, or this Coulomb branch description. And it turns out that these infrared methods are very powerful in in encoding the symmetry TFTs. Moreover, these can include like enhanced. So it would be nice to include like enhanced symmetries like the SO3, the U1 instant of a symmetry that enhances to SO3 for example, for the SU2 5-dimensional theory, for the E1 cyber theory. It would be nice to encode two groups or higher groups, as well as non-invertible symmetries, as I highlighted already. And finally, I told you about the Coulomb range description, and why one can derive the symmetry TFTs from the Coulomb range description. But what about the X branch symmetry TFTs? Can we derive the symmetry TFTs from the X branch? And can we also understand non-trivial aspects of these CFTs by deriving the symmetry TFTs in the X branch? And with this, I thank you for your attention.
All right, let's thank Fabio. Questions?
Sorry, I have just a general question. How much of these results depend on supersymmetry?
So for the example I show you, it looks like they depend on supersymmetry, but not really. So let me give you an example. Suppose that there is a system which is non-supersymmetric and is related by to a system which is supersymmetric by a deformation, for example, with a form such that with the form of SCFT such that we break supersymmetry. As long as this deformation doesn't mix up with the symmetry that we are studying, I think these are good techniques that can be applied to this non-supersymmetric system. Of course, you have to find, which is not easy, a non-supersymmetric system that is related to a supersymmetric one by a deformation that doesn't screw up with the symmetry that you're studying, the anomalies.
Thank you.
Fabio, can I ask a question?
Yes.
Suppose that you have a theory with two group which has a mixed anomaly with other symmetry. Does this method kind of tell you how to turn on the background, which is a combination of two things, of course, because there's two group, how to write down coupling?
So let me try to understand. Maybe okay, let me try to understand the question. So you're asking whether one can derive from the symmetry TFTs whether
exactly
the two group background, for example, delta B2 Bok.
Yes,
Bok.
yes. And not just that, but how you write down the combination. Because if it's two group, you have to have a background field for one form symmetry, and
right.
Something like Stephen Whitney class for the flavor symmetry, right? Is that automatically come out of for example, subtractive approach, or?
For this discrete, when they involve a discrete one for symmetry, it can be tricky. But what we can do, you can study, for example, you can study background for this structure group. So you study background for this full structure group, which are related to the two group.
Does it come out automatically from the geometry?
These I don't know whether okay. There are so approaches which I'm not super familiar with, which have been discussed in this two recent paper to whether these come out from geometry. This is not clear yet. I think it's not yet set in stone. But more than really deriving this condition, I think what you derive from this approach is a necessary consistent condition by studying the backgrounds for this structure.
Okay, thank you.
Which is consistent with this. Yes.
Do we have more questions? So I have one more generally about the symmetry theories. What are the conditions on this to be, like what would be the conditions on a topological field theory to be a symmetry field theory? Is there one, or?
Good. This is a very good question. I think right. So a couple of months ago, I would announce where these have they have to have at least this digraph width and term or BF term.
Mm-hmm.
And of course, they need to have the background for the symmetry that you want to study.
Yeah, sure.
However, more recently, there have been like I think it's not a published result, but I think this is not true. This can be generalized, especially in the case of non-invertible symmetries. On invertible symmetry, these can also not be of digraph width and type or BF type, but rather, I mean, they're not very. I mean, they're somehow twisted generalization of that theory. I mean. But I think that, you know, sort of that theory or generalization of that term should be contained. And then you can have, of course, anomaly coupling. And as long as they are topological, I think it's fine.
All right. More questions? If not, then...
Question about the symmetry TFT. So if I understand correctly, if you have a theory with a mixed and not with an anomaly, you should think about it not as a boundary for the sim TFT, but a gapped interface with an SPT phase. Does that picture fit in with the string theory constructions about how you think about the symmetry TFT?
I'm not sure. Right. So I'm not sure whether it. I think it enters, but I'm not sure how it enters.
Okay.
I mean, my point of view was more like, you know, down to earth. Like we get these topological couplings, and then of course they correspond to anomaly because we know because they are topological and they are. Then you can say what that they correspond to, you know, gap SPT phase. But it's more like the way I think it's more like a posteriori comment rather than I'm input this from the beginning. I don't know whether I explained myself, but.
All right, thanks.
Okay, any more questions? If not, then let's thank Fabio again.